When it comes to aerodynamics, NASCARs are some of the most underrated objects. They might look simple, but there are so many minor aerodynamic features that make huge differences to the car's performance, as you can see in figure 1 with all these little things here. And actually, the aerodynamics in NASCAR are very underrated too. They're not just a bunch of putzes, they're actually really good. I mean, I actually haven't worked in NASCAR, so I don't know from personal experience, but I can't compare them with other automotive aerodynamic fields that I have worked in, but just looking at their final products, they look like they know what they're doing. And one thing that is challenging for them is accurately simulating the aerodynamics of their cars. What approach should you take? Which approach is adequate? That is what we're looking at today in this podcast, and we're going to cover in this paper a few different CFD approaches and see what one performs best. Actually, in the process, we will see a bunch of information about the different aerodynamic devices on NASCARs too, so there's a lot of juicy stuff coming. So this paper is called Effectiveness of Scale Averaged RANS and Scale Resolved IDDES Turbulence Simulation Approaches in Predicting the Pressure Field over a NASCAR Race Car. So this is open access and you can find it in the link below. And the motivation for simulating a NASCAR instead of using a wind tunnel test is the same old chestnut, where wind tunnel tests are more expensive and use more resources. So if we can use CFD, then that will allow us to do more with less. In addition, the NASCAR governing body limits how much wind tunnel time a team can use, but as a nice twist, they also have a limit on how much CFD teams can use per month as well. So it's also not just about using CFD, but using it more efficiently. So as such, in CFD, the aerodynamicists are left with a choice. Is RANS a better choice or is DES a better choice? And just a quick explanation of the differences for those who don't know. So RANS stands for Reynolds Average Navier-Stokes, and this is the most basic Navier-Stokes CFD solver. They are very quick, but the least accurate. DES, on the other hand, is a hybrid between RANS and LES, and LES is a much more accurate, but it takes a longer time to do it. It's much more accurate in terms of its results. So DES is a half step up in effect. It isn't the full step up to LES, but it is much better than RANS usually. So it incorporates a little bit of LES, usually when you're far away from the wall enough to trigger the LES requirements. So these researchers are looking at a bunch of variations to the CFD approach with RANS and DES to see if the additional time required for DES is worth it from an accuracy point of view. And to determine this, the researchers aren't just looking at general coefficients like drag, lift, and side force, but also the flow physics and the accumulation of forces as you progress over the car, which is a nice addition. We'll see some really cool figures later on. So while NASCARs might look very much like passenger cars, the authors say that, aerodynamically speaking, they are very different. For example, a typical passenger car might produce a lift-to-drag ratio of about 0.3. So yes, they are actually producing a little bit of lift and not downforce. On the other hand, a NASCAR produces a lot of downforce and a downforce to drag ratio actually of around 2 or more. So -2 lift to drag ratio. So it's a lot different. So not only is the vertical force to the drag ratio much greater, but a NASCAR produces downforce instead of lift. And that is what I mean about NASCARs. They have a lot of very nuanced surfaces that do a lot for the car. They may not seem like much, but they definitely change how a regular production car goes around a track. So one thing I really like is that these researchers say that even in wind tunnel tests, the values you are getting are not entirely representative of every real life condition because wind tunnel flows are usually very limited, and not to mention that each wind tunnel is actually different. So each wind tunnel has its own flow, and in fact, this is a major difficulty that many automotive manufacturers have, because if you take your car from your wind tunnel and then it might give a certain aerodynamic value, but then in another wind tunnel, it might give a few percent different. So in fact, back in the 90s and other times as well, there was an effort in Europe, for example, to take the exact same car around to all the different automotive wind tunnels in Europe and see what the lift and drag coefficients came out to be. And the variation was very surprising at the time. A lot of people didn't realize that wind tunnels do give different drag and lift values. So that leads to the point that when a manufacturer quotes a certain drag coefficient, for example, it doesn't necessarily mean that that car is better than a rival's just because that rival quoted a higher drag coefficient. It could be that the wind tunnel that the rival tested their car in gave worse drag coefficient results. So CFD also has the potential of being more accurate than wind tunnel tests in its reliability if an accurate model has been developed, though. If it hasn't, then CFD is not really worth very much. So you need to get an accurate model, just like in wind tunnels as well. You need to have an accurate method as well. So for their turbulence model, the researchers made it a point to highlight that they used the SST-K one, which is good. That is the turbulence model you should be using for this type of object. And they say that they will rely heavily on validation data from their wind tunnel to verify the accuracy of their CFD, which we'll see later. But first, in table 1, we see the NASCAR configuration, the researchers tested. So they labeled them configurations C1, 2, and 3. C1 and 2 are when the car is yawed to 3 degrees, which is really cool to see because you almost never see research on yawed cars, despite it being so common during driving anyway. So those results will be cool to see. And as I said, while this research is about which CFD method to use, in addition to that, we're going to see a bunch of aerodynamics too. Now, the difference between C1 and C2 configurations is the splitter gap is low for C1, as shown in figure 3 down here. So that's the low, that's the ground here, and then that's the splitter plate just up here in the white. And the splitter plate is closer to the ground in C1 than C2, which is on the right here. C2 is higher off the ground. Typically, C2 is expected to produce less downforce if everything follows typical trends, that is. We'll see later if that happens too. Now, configuration C3 is for the car not yawed and with a high splitter gap distance too. So pretty much the same as C2, just not yawed, it's straight. So in figure 2, we see the amount of yaw of 3 degrees is very noticeable. You can definitely tell it's yawed. So one thing to note is that this research is for a Gen 6 NASCAR. And in addition to the various CFD approaches they are considering, they are also looking at how compressibility affects the CFD results, which is awesome because compressibility effects are so overlooked. I mean, in one of our YouTube videos called When is Air Compressible? Aero Fundamentals number 48, I go through the math of how speed affects air density, and in that video, you'll see how the about 100-year-old rule of thumb that if you go over Mach 0.3, then you treat the air as compressible, and under it, the air is incompressible. It's actually not that reliable these days. In fact, there's a strong argument that even over Mach 0.1, the air should be treated as compressible. And this is one of the major problems in the automotive industry now, in that the standard is to use incompressible solvers, despite strong evidence that you should go compressible. And so when they complain that they can't get accurate results, well, yeah, of course you can't get accurate results, because if you need your CFD to be within 1% error, but that is already eaten up by the 1% error in the compressibility effects, then that means everything else has to be completely perfect just to get that 1% error that you need. So there's a major underlying assumption that is wrong there, or potentially wrong. I mean, the math is definitely working out, and we'll see in this paper as well if it potentially is as well. So I'm really happy to see these researchers have covered this aspect, and I can't wait to see what they found for their NASCAR. And just keep in mind that when you see an I after something like RAS I, that means that is for incompressible. And when you see a C after something like RAS C, then it is for the compressible counterpart. And just mentioning CFD facts, for their surface mesh, for their NASCAR here, they used 13 million cells, which is quite a lot and good. And for their domain, they used a huge one, far larger than what is typically used. So it was 211 times the length of the car, 200 times the width of the car, and 200 times the height of the car. And that is a very interesting setup, because they say that the massive domain was used to make the car perform as if it is in an open road condition. Well, that is great, but there are a couple things to consider. The first one is that a typical NASCAR operates quite close to a wall. So this domain isn't representative of that racing condition because the wall is missing. But you could argue that this is just a general investigation into NASCARs, which I definitely get, and sure, the large domain designed to replicate a complete off-road condition is still good, but now we come to the real problem, that is the validation data. So the validation data comes from a wind tunnel, and a wind tunnel is never that big. So the validation data has walls affecting the results, and then you use the validation data to validate your CFD, which means you've got your wind tunnel, which is not open road, and then your CFD, which is open road, and that is going to change the results. So right there, the CFD and wind tunnel setups are wrong. They're different. So naturally, you won't get the same results. And this really brings us to a CFD principle that every CFDer needs to keep in mind, and that is, when you are doing a high-level CFD simulation, you need to match your setup with validation data setup. Otherwise, you're comparing apples with oranges. And the greater the difference is in the setups, the greater the discrepancies will be as well. So in this particular case, I don't think it will be that bad. I mean, there might be a percent error because wind tunnel setups are usually pretty representative of open roads because of the blockage ratio is low. But we will see what it is for this setup, and then we'll have more information to better determine how much of a discrepancy there would likely be. So let's move on. So the CFD was done at 150 miles per hour, so 67 meters per second. And at that speed, the flow is very compressible already. As I said, even at Mach 0.1, there is a 1% error in the density of air. So this is at about Mach 0.2, and that error is much higher. And in our YouTube video, we go through the math of it. So good thinking from these researchers to consider the compressible solvers too. One thing about their CFD setup that I don't quite understand is that they say that to emulate the contact patch that forms between the tire and the ground, they used a small vertical wall. Now, I'm not exactly sure what they are referring to when they say this, because there aren't any figures highlighting the setup. Maybe they need this setup, and from this brief description, it refers to simply a wall popping up a little off the ground, and that touches the tires, which I could be wrong with how I'm interpreting this, but that is what it seems like. And this wall is stationary because their wheels are stationary from what I can tell. So if they had their wheels rotating, then the small vertical walls wouldn't be necessary. So I don't know exactly what they mean by this part of their setup's discrepancy. Anyway, then they modeled the radiator flow as going through a porous medium to accurately simulate the cooling flow. So that's pretty good. Now, the turbulence intensity was 1%, which is slightly better, or a bit better actually, than what most automotive CFD and wind tunnels use. This 1% is far more real life as you'd get, which could be as high as 10%. And yet, despite this turbulence intensity being so high, it still doesn't approximate a real race because you get wake from other cars too. So this is really an ideal situation where you are so far ahead of the pack, or maybe it's the worst case situation where you are so far behind the pack that the wakes have died out by the time you reach the other cars, by the time they reach the car. Anyway, this shows that just how many conditions you need to consider to get an accurate representation of the car's aerodynamic performance during a regular operation. And one thing to point out is about their mesh. So they use a meshing system where neighboring cells only ever change by a factor of 2. So for example, if you have one cell that has a width of 1 millimeter, then the cell directly next to it can only ever be between 0.5 millimeters and 2 millimeters. This is a really good approach because it limits having large discrepancies between cells. And the reason why having large disparities is not great is because the more cells you have feeding into one cell, the more information you're having feeding into one cell from many cells. That means you will lose some information because the biggest cell can only have one value, and that value will be some mix of the inputted values from these other smaller cells. So having the cells change more gradually helps keep the information more refined and accurate. Another cool thing that these researchers did was to use various properties in the field to know where to refine the cells. So for example, if you have really high thermokinetic energy or really high rates of change, then you can tell the CFD software, hey, refine more in that region so you can better capture what is going on and then have a more accurate simulation. So that is good thinking by the researchers. Now, the Y plus value was below 1 over the entire car, so that's really good. And interestingly, they say that the final RANS and IDDES meshes were 130 and 200 million cells respectively. Now, that is a little surprising that the RANS mesh was so close to the IDDES mesh, but we'll see later how the results are affected by the different mesh finenesses as well. Let's first talk about time stepping because these authors cover some good details about how to select the time step for your simulation. So if you are using a steady state approach, these time steps are not relevant because it's steady state, there's no time really. But if you're using unsteady CFD, then time steps can be the difference between an accurate simulation and a simulation that would even just crash. So these authors used the current number as the guiding light for their time step selection, and they selected a time step that results in a maximum current number of 1 in their entire domain. So everywhere in the domain, the current number was equal to or less than 1. Actually, it was less than 1 here. It's not equal to even. So as a physical interpretation, that means that you won't get bits of air jumping more than one cell each time step. That is good because it means the turbulence and interaction between bits of air are better captured and resolved, hence a more accurate simulation. And as a general rule, you should have your current number less than 1. Another interesting factoid is that for each time step, they had 6 inner iterations, so the residuals would drop by 3 orders of magnitude or more, I guess. So this is an overlooked setting, and what this refers to, this inner iteration, is when you have your simulation and you step forward one time step, The simulation doesn't then just step forward and again another time step after that. What actually happens is that your simulation steps forward one time step, and then you iterate through without the time changing. And then once you've iterated through either a predetermined number of times or that the residuals are below the threshold you want, then and only then the CFD will step forward again. So this process of iterating while keeping the time step constant before taking another time step is referred to as the init iterations. Here they have 6 init iterations, which means that the simulation takes one step forward, then holds the time steady, iterates through 6 times, then it takes another time step. And I just want to go through that because this process explicitly, because some softwares don't actually show the process. And as such, sometimes people don't even know about this step in the simulation. So if you didn't know about that, hopefully my brief description here made it clear what is happening. Anyway, moving on. Now, we really come to a section that really impresses me. So these researchers, the computing resources they had was literally just a 144 core cluster. So just 144 cores. To run their CFD simulations on this cluster, the RANs took apparently 40 hours, and then the IDDES took 600 hours. Now, I'm not sure if that's just for one simulation, so the RANs took 40 hours per simulation and the IDDES 600 hours. I mean, from my experience, one IDDES simulation with 200 cores, 200 cells on 150 cores, should take about 200 hours or so, but that also depends on the quality of the cores. On the other hand, they did a number of simulations, so I don't think you could get all the IDDES simulations done in just 600 hours. So I don't know. If it is just 600 hours for all IDDES simulations, then that's pretty good. If it was 600 hours per simulation, then that is insane. And this research would take forever to do. And the more I think about it, actually, the more I think that it might have taken 600 hours per simulation. So if so, then hats off to these researchers for their persistence. Let's now look at the grid independent study because they have pretty interesting results. So in figure 4 here, we see the changes in the drag and lift coefficients in the left and right figures respectively. These data points are for the coarse, baseline, so medium, and then the fine meshes. These were for the 3 configurations of the NASCAR, so C1, 2, and 3. And note that this was for the compressible RAN solver, so not the IDDES, so RAS-C. And the y-axis here is for the difference in the percentage between the CFD and the wind tunnel results for the drag and lift. One thing to note is that the mesh wasn't refined too much between finest levels. They just bumped it up by 10% each time, which is pretty low. It should be more like 100%, especially if they were to do IDDES, which they don't here. Anyway, the meshes don't seem to converge. I mean, I don't really see much difference if you were to take the coarse or even the fine because the data just drifts around a lot. I mean, there's no plateauing going on. So I think the baseline is kind of an arbitrary selection and they could have even just gone with the coarse from what I can tell here. Having said that, going from the coarse to the fine at most changed the results by a couple percent, so not that much either. What's more, sometimes the results didn't get better by 2%, but got worse by 2%. The lines just didn't plateau. So I think that selecting the baseline mesh for this grid independent study was fairly arbitrary. But I definitely understand why they didn't go finer because it would have taken so long to do a simulation. Already 40 hours for this RANs. That's a really long time. So they were very limited in how much finer they could go. So let's move on to their validation study. So in figure 5, we see the drag and lift coefficients in the left and right respectively. The compressible and compressible are both given, which is cool. So you have C and I, which stands for compressible and incompressible respectively. And surprisingly, the RANs results are much better than the IDDES results, but we'll see later if that is actually the case once we dig more into the results and not just the superficial overall drag and lift values. But as for the incompressible versus compressible, the compressible solver consistently gives better results. The author suggests that this is because the compressible solver better predicts the flow in regions of locally high compressible flow, for example around the splitter. This is an expected result, but unfortunately the researchers don't go into the flow physics later on for the difference between the two. So at the moment it could just be better overall results, but for the wrong reasons we don't know yet. As a constellation, in figures 6 and 7, they give more overall values which help in increasing the certainty that the compressible solver is better. So let's go through them now. So in figure 6, we see the front and rear lift coefficients, CLF and CLR. And at least for the front lift, that the compressible solver is doing better again and by a few percent all the time. For the rear lift, it is a little inconclusive. Now, in figure 7, the researchers give the amount of lift the front produces as a percent of the entire car's lift, and this kind of just compounds the potential errors from figure 6, particularly in the rear. So I don't think this graph is too reliable, perhaps just as a general idea. As for the lift-to-drag ratio, as given in the right figure, the results are again inconclusive. So overall, I would say that the compressible solver is likely better than the incompressible solver, but we need more information about the pressure distributions or wakes to make sure that the flow physics is more accurate too. We're not just getting the good overall results for bad reasons. But that's not all the information we can get out of these graphs, because they also show the results for 3 different NASCAR setups with 3 different colored lines accordingly. And across these 3 figures, just in general, it looks like C1 configuration is pretty much always more accurate. So C1 is the orange line here. And just as a reminder, if we go up to table 1, C1 was the configuration with a 3-degree yaw, I believe. Let's quickly go back up there. And so we have 3-degree yaw and a low splitter gap. And the C2 configuration, which is exactly the same as the C1, but it has a high gap for the splitter. So that figure there, it's higher off the ground. And then C3 is exactly the same as C2, but is now no longer yawed. And C2 configuration has a much worse drag and lift from figure 6, I believe it was. So down here, further, here we go, see figure 5. It has a much worse lift and drag, as well as the front and rear lifts. So C2 is much worse in terms of the accuracy. So that tells us that the underbody is probably the thing giving the researchers the willies. And actually that's foreshadowing what's to come. We'll see the underbody later on, and yeah, anyway, let's continue here. Having a lower splitter plate helps mitigate the nuances of the underbody flow, at least that's what I think. So it makes the simulation more accurate to have it lower. That's what I'm seeing here. Now things get even more juicy because C3, which is where the NASCAR has a high splitter, but is now straight instead of yawed, this performs even worse. So the blue line. That is a little surprising to me because straight is usually easier, but then again, perhaps the Aero devices on top of the roof of the car, as you can see in figures 1 and 2, make it harder perhaps when it's straighter because these devices are at an angle. So when you put it straight, it maybe causes some potential problems there. So these devices up here. So from here, the authors seem to deem the compressible CFD results as the ones to look at, and they only present them later on, the more data about them. The incompressible ones are tossed away like yesterday's ham. Also, for figures 8 and 9, there isn't any wind tunnel data, so what we are going through now, I think, is more just general information and shouldn't be taken too seriously. So down in figure 8 here we go. This is figure 8. We see the accumulated drag, lift, and side force coefficients along the entire car from the front to the back. For the drag coefficient, we see, as expected, a huge spike at the front because the front is ramming air and causing high pressure there. Then over the rest of the car, there is little more drag until we get to the back, where the drag just jumps up a lot. So from this figure, we get the expected information, and in that the front and rear are the main contributors to the drag, and that the drag coefficient of this NASCAR is about 0.5, but interestingly, over the back window, the drag drops a lot. So the rear window region / the underbody in this region is producing effectively thrust. One interesting thing is that it isn't often talked about how the sharp rear spoiler just juts up. I mean, look at that, how much it just goes up. This looks very unaerodynamic because sure, the flow hitting it will be pushed up a little, but it is more like a blunt object than anything that will just cause a lot of drag. But what happens here is the air coming along will hit it, increase in pressure as some of the dynamic pressure is converted into static pressure, and then over the trunk, there will be a lot higher pressure, which means that you have all this air here, which is high pressure, pushing the car down into the ground more. It's an ingenious design that dramatically increases the downforce, but that also comes at the cost of the larger drag increases as well, which it is contributing to. Moving on to the lift coefficient, there is good downforce consistently being produced over the entire length of the car. The front produces a lot of downforce, which is mainly because of the splitter plate. Then even the front shield region produces some downforce as well, that's pretty good. Then as expected, the rear, because of the diffuser, is producing more like a third of the car's overall downforce. Moving down, the side force coefficient is pretty interesting because even when the car is straight, there is still some side force, which is because, again, the asymmetric aero devices on the roof of the car and around the car as well. Now, when the car is yawed, so these blue and red lines, the car produces even more side force, and that is actually good when you have to go only one way and have to only turn one way. That side force can help you do that. Now in figure 9, the graphs show pretty much the same information, but just presented as deltas between the RANS and the IDDES simulations. And because we don't have any wind tunnel data to compare the CFD to, we can't really tell too much anyway. So let's move on. Now in figure 10, we see a really well presented figure. So we have the splitter plate and then the 5 pressure port locations, P1 to P5. The colored lines correspond to the pressure coefficients at the points from the wind tunnel, which is green, then from RANS compressible, which is red, and then from IDDES compressible, which is blue. And there are a lot of really interesting things about this paper and impressive things about this paper, and this figure's presentation is just another one of them. And this is what I meant earlier, how NASCAR aerodynamicists don't get nearly as much credit as they deserve, because everyone just looks at NASCAR and looks how they just drive around in ovals and not much is happening, so the aero must be primitive, right? But having worked in the automotive aerodynamic fields, I'm inclined to say that NASCAR aerodynamicists are better than most. Now in this figure, the RANS CFD produces fantastic pressure coefficients almost identical to the wind tunnel. The DDS does great at the sides, but when you get to the middle, so this blue here, it doesn't do so well. The author suggests that this is because the DDS is predicting a separation bubble over the middle, which is increasing its pressure, so just around here. So from this figure, the RANS is better for the splitter plate than the IDDES. But looking at the back of the splitter plate structure, neither the RANS nor down here, neither the RANS nor the IDDES does a good job. They're both about just as wrong as each other. You can see we have some pressures back here. They're both pretty different to the wind tunnel. Now in figure 13, we see pressures along the left side of the car, the left bottom side here, and the DES starts to come back here and do a better job than the RANS. Then for the rest of the figures up to and including figure 23, the CFD is kind of hit and miss. Sometimes it's good, sometimes it's bad. There's nothing really consistent about it, and the RANS and IDDES don't really outweigh each other. They're usually just as, higgledy-piggledy as each other. At best, sometimes the trends are the same. But then in figure 23, we finally get some good agreement. So figure 23 is down here. And both CFD approaches give accurate pressure coefficients over the entire top of the car from the front all the way to the trunk. Then in figure 24, again, both CFD approaches give very good results over the left side of the car. And then likewise in figure 25, they give good results over the right side of the car. So it really is a case that for this study, the CFD does a much better job for over the exterior of the car than in the underbody. The underbody is just all over the place, as we saw in the other figures. And that brings us to the end of this podcast. I found it really interesting, and I thought that we can conclude that the DES is probably a little more accurate. However, I think a better grid independent study is needed. And also, when we saw a few percent increase in the accuracy of the DES, is that really worth the 15 times more simulation time for the DES compared to RANS, considering that you have a limit of your time that you can do CFD? Perhaps not in this particular case, but for other situations, DES is better. So if you like this video, make sure to hit the like and subscribe buttons. And in this podcast, we went through a lot of CFD and theory. If you want to learn more about CFD, and there's a lot more to learn, check out our courses in the link below. And if you want to learn OpenFOAM, which is a really good and completely free CFD software, but hard to learn, then take our course in the link below. We go all the way from complete noob all the way to advanced, like overset meshes and dynamically morphing meshes. And if you are doing experiments, did you know that you probably have a 2 to 4% error in your data and you don't even know about it? That is because of the changes in the atmospheric conditions, which you can't control. But in the atmospheric course link below, we go through how to get rid of these errors still. So check that out. Peace out, amigos.